Okay, get ready for this. What if the walls of our buildings could heal themselves, cool our cities, and maybe even think? It sounds like something straight out of science fiction, right? Well, a brand new paper has just dropped a detailed blueprint for exactly that, creating structures with a real, functioning, living skin. And we're not just talking about putting more plants on buildings. We're talking about completely rethinking what a building can even be. Just think about that for a second. Instead of concrete and glass being this hard line separating us from the natural world, imagine a responsive, breathing membrane, one that actually interacts with the environment, blurring the lines between what's built and what's natural. This is way more than just a cool idea. It's an actual engineering framework designed to make this happen. Of course, you have to ask, if this is such a great idea, why aren't we already living in glowing organic cities? Well, the reason it's been a dream for so long is that a living skin has to do a few things that seem to completely contradict each other. It's a classic and really tricky engineering puzzle. So here's the core of the problem, the big challenge. A perfect living skin needs to do three things at once. It has to think, which means processing information. It has to self-cool, pushing heat away. And it has to self-heal, repairing any damage. Now, for a long time, the thinking was that these goals were just mutually exclusive. I mean, how can something be dense enough to heal but also porous enough to cool itself? And how can it compute without generating a ton of heat that messes the whole system up? That's been the roadblock. And this is where the paper makes a really clever argument. It says we've been looking at this all wrong. It's not some impossible trilemma, a fundamental law of physics that we just can't break. No, it's a design tension. It's a really hard engineering puzzle, for sure, but it's one that can be solved. The goal isn't to cheat physics. It's to design a system so smart, so elegant, that it works with physics to hit all three goals. So how do you actually solve this puzzle? Well, the paper proposes this incredibly elegant blueprint, an architecture with a very specific name, and this name is basically the instruction manual for engineers trying to build this thing. It's called the RHOS architecture. That's RHOS, and it's not a random name at all. Each of those letters stands for one of the four key functions, the four tools in the toolkit, if you will, that make this whole living skin concept possible. This isn't magic. It's a step-by-step, constructive path toward a pretty incredible goal. So let's open up this RHOS toolkit, shall we? We're going to look at each of the four core operators one by one to see how they all work together to solve that big design tension. Let's start with R. First up, R is for repair. This is the self-healing part of the equation. Imagine using biomaterials like mycelium networks or special enzymes that actively seek out and fix tiny cracks, fight off aging, and just generally keep the building's structure sound. You can basically think of it as the structure's own built-in immune system. Next in our toolkit is H, and that stands for heat evacuation. This is the self-cooling engine. The surface is designed to be incredibly efficient at radiating heat away, basically beaming it out into the cold of space. This process is called passive radiative cooling, and it's so good it can actually achieve sub-ambient temperatures. That means the surface can get cooler than the air around it. And the best part, it does all this with absolutely zero power. Then we get to O, for optobiological control. Now this is the brain. It's the skin's nervous system. But forget about copper wires. This system uses light, guided through biological channels to send information. Seriously, think of it like living fiber optics. It's a ridiculously fast and energy-efficient communication network that's literally woven into the fabric of the structure. And finally, we have S, which is for storage. You can think of this as the system's shock absorber. It has built-in buffers for things like heat, water, and even data. So when there's a sudden heat wave or a massive flood of information, these layers just soak up the impact. They make sure the whole system stays stable and doesn't get overwhelmed. Okay, so we have our four components: repair, heat evacuation, optics, and storage. But how do they all fit together? It's not just a random mix. The architecture is based on a very specific and really intelligent layering system. The components get assembled in this really precise stack. So from the outside looking in, first you have the heat evacuating skin. That faces the environment. Right under that, you've got the biooptical nerves for communication. The core of the whole thing is the self-repairing layer, and then the innermost layer is where you find the storage buffers to keep everything stable. The order here is absolutely critical. Each layer is designed to support the others so the whole system can work. All right, I know what you might be thinking at this point. This all sounds incredibly futuristic, maybe a little too good to be true. And yeah, it is super ambitious. But the authors of this paper are really clear that this is not just some sci-fi fantasy. It's a practical blueprint for a testable, real-world engineering project. This quote from the paper itself really says it all. They're not claiming they've broken any laws of physics. Instead, what they've done is create a constructive design. That means it's a step-by-step plan that gets you closer and closer to the perfect solution. And importantly, it's falsifiable. That's just a scientific way of saying it comes with clear, measurable goals, so we can actually test it and see if it's working. And we're not talking about vague goals here. These are hard, specific numbers. The skin has to radiate more than 80 watts of heat for every square meter. It must need less than 12 minutes of manual maintenance per square meter per year. Every single part of this design has a concrete target to hit. Let's just zoom in on one of those for a second, because it's wild. A repair balance of 95% or higher. What that actually means is that the skin has to be able to heal itself at a rate that's almost identical to the rate at which it breaks down from aging and damage. I mean, that is an incredible target. We're talking about near total self-sufficiency. Now, to make the end goal crystal clear, the designers did something that I think is just brilliant. They defined failure. They created a benchmark for the absolute worst case scenario, and they call it the hell state. And trust me, it's not just a catchy name, it's actually a super important diagnostic tool. You can really see the difference here. The hell state is a system with high entropy. It's chaotic, it's inefficient, and it needs constant work to keep it from falling apart. On the total opposite end, you have the ideal corner, a highly ordered system that needs almost zero maintenance and wastes practically no energy. So the goal for an engineer becomes incredibly simple. Get as far away from the hell state as you possibly can. So the big takeaway here is that this is so much more than just a new way to build stuff. It's a blueprint for a whole new relationship with our environment. And it forces us to ask a really deep question. Are we moving out of an age of just constructing cities and into an age of engineering entire ecosystems? If this blueprint really works, the answer isn't just yes. It's that the future of architecture is quite literally alive.